This is the video on molar mass. So remember, in every weekly review code, there will be two codes. One will be a written code on the screen. The other will be a verbal code said by myself. Each code will be 3 numbers, and they are random numbers. You will need all the codes in order to move on with the homework assignment. So here are the instructions. Remember, right when you're going through this, just look for what's written in green. That way you can, it's just summarizes what you need to know. So this is the weekly review written code. I recommend you write this down somewhere. All right, so let's just take a look at atomic mass. Now, we've already looked at atomic mass before. It is the mass of a single atom represented in units of AMU, or atomic mass units. Now, these are the masses on the periodic table. Now, these are all average atomic masses based on, the number and percentage of isotopes. But let's get some practice finding the atomic mass. So the atomic mass of hydrogen, well, 1.01 atomic mass units. What's the atomic mass of carbon? 12.01. Atomic mass of oxygen, 16. And gold, you can see that we've got more massive elements like gold, 196.97 atomic mass units. So now let's take a look at molar mass. Now, molar mass is the total mass of all atoms present in a formula. It's also called formula mass. So if you see this written down somewhere, so these are usually interchangeable. Formula mass. The unit for molar mass is grams per mole, which is the same thing as atomic mass units. There's a little difference, but for these purposes, we can just say that these are interchangeable. So let's do an example with table salt, also known as sodium chloride, or NaCl. So what elements make up this model? Make up this molecule. It's just sodium and chlorine. So what is the atomic mass of each element? So notice up here, I just need the atomic mass of each element in grams per mole. And then how many of each element are in this molecule? Well, there's only one of each. So I just multiply the atomic mass times the number of each, and then I just add them all together, and I get the molar mass of sodium chloride. So let's get some more practice, right? Let's take a look at dihydrogen monoxide, also known as water. So what elements make up this molecule? Well, it's going to be hydrogen and oxygen. What is the atomic mass of each element? So you can see here that hydrogen is 1.01, oxygen is 16. How many of each element are in this molecule? So I've got H2O. I have 2 hydrogens and 1 oxygen. So now we can use this to calculate the molar mass of this molecule. Hydrogen is 1.01, oxygen is 16.00. I've got 2 hydrogens, so I multiply the atomic mass of hydrogen by 2, and I get the total, the element mass in that molecule. And then I only have 1 oxygen. I just add these two together, and I get 18.02 grams per mole. So now let's take a look at lithium sulfide. So I've got 2 lithiums, 1 sulfur. So I've got lithium and sulfur. What is the atomic mass of each element? You can see, just get those off the periodic table, right? So I've got lithium is 6.94, sulfur is 32.07. How many of each element are in this molecule? I've got 2 lithiums, 1 sulfur. And the molar mass, well, I just do the same thing, right? Now I have 2 lithiums. I multiply 6.94 by 2. And I get 13.88, and I add that to that sulfur, and I get 45.95 grams per mole. So let's take a look at aluminum chloride, AlCl3. So I've got aluminum and chlorine. I've got 1 aluminum, 3 chlorines. So now I do the same thing I've been doing. I just look on the periodic table. I can find the atomic mass of aluminum and chlorine, but I multiply chlorine by 3, add those two together, 133.33 grams per mole. So now we can get something a little more complicated, but it's the same process. Let's take a look at glucose, C6H12O6. So it has carbon, hydrogen, and oxygen. I just look on the periodic table to find the atomic mass of each of these. And the number, well, I've got 6 carbons, 12 hydrogens, 6 oxygens. I just multiply the atomic mass of each of those elements by the number of each of those, and I get the total amount in for each of those elements, add them together, and this is just regular glucose, like sugar. So 180.18 grams per mole. So same process for anything. So if you can do one of these, you can do any of them. Now, back to this original question. We've heard of molar mass. We know grams per mole, but what is a mole? So let's just compare a couple of things. Let's look at elephants and donuts. Let's just say we have a dozen donuts and a dozen elephants. So what does a dozen mean? So If we got a dozen eggs, dozen donuts, that means 12. It is just a number. That's all a dozen is. So how would 1 dozen elements be similar to 1 dozen donuts? So I would have the same amount, right? If I had a dozen elephants, dozen donuts, you could say, well, I have the exact same amount of elephants and donuts, right? I've got 12 of each. But how would 1 dozen elephants be different than 1 dozen donuts? Well, think about it this way, right? Hold a dozen elephants in one hand and a dozen donuts in one hand, right? Or in the other hand. You couldn't hold a dozen elephants in one hand because it's too heavy. So a dozen elephants weighs a lot more than a dozen donuts. So you have the same amount of each. There are 12 elephants, 12 donuts. However, 12 elephants weigh a lot more than 12 donuts. So let's take a look at the mole. A mole is the amount of a substance that contains exactly 6.02 times 10 to the 23rd things of a given substance. So just like a dozen is 12, a mole is 6.02 times 10 to the 23rd. It's a very large number. It's Avogadro's number. That's what we call it, 6.02 times 10 to the 23rd. So this is our attempt to be able to calculate the number of atoms or molecules like on a larger scale, right? So this is why it's this number. This is why it's not like 10 times 10 to the 23rd or 6 times 10 to the 23rd, why it's 6.02 times 10 to the 23rd. And it goes past that. It's like 6.022 something something times 10 to the 23rd. But the mass of an atom in grams per mole is numerically the same as the mass of 1 mole of atoms of that element in grams. So 1 atom of sulfur has a mass of 32.07 grams per mole, or atomic mass units. So 1 mole of sulfur atoms has a mass of 32.07 grams. So what that means is that let's just look at that number. Let's just say I've got sulfur atoms, right? I've got all, and I can count them. 1, 2, 3, 4, all the way up to this number. And I'm putting all these atoms on a digital balance, on one of those digital balances. Once I get to this number, 6.02 times 10 to the 23rd, well, that scale would read this down here, 32.07 grams. So I could look at that amount and say, I know exactly how many sulfur atoms are in that amount of mass, right? That's what a mole is. That's what Avogadro number attempts to do. So now let's take a look at helium and lead, right? So how would 1 mole of helium be similar to 1 mole of lead? It's the same amount, right? The same number of atoms. How would it be different? Well, notice, look at the helium atom. The helium atom is really small compared to the lead atom, right? The lead atom is one of our larger, stable atoms. It's very large. Well, the lead atom is like the elephants. The helium is like the donuts. 1 mole, if I had the same amount of each, 1 mole of lead is going to weigh a lot more than 1 mole of helium. So which has more atoms? This is kind of a trick question. 1 mole of helium or 1 mole of lead, they're going to be the same. It's like saying what has more, 1 dozen elephants or 1 dozen donuts. They're the same amount. Which weighs more, 1 mole of helium or 1 mole of lead? It's going to be the 1 mole of lead because the lead is like the elephants. I've got the same amount of each, the same number of atoms of each, but lead weighs more. Look how large a lead atom is compared to the helium atom. So what is the mass of 1 mole of helium? So remember, if I'm taking individual atoms, I'm counting 1 mole of each, 1, 2, all the way up to 6.02 times 10 to the 23rd, and I put it on a scale, 1 mole of lead or helium atoms is going to have a mass of 4.00 grams. Now, if I did the same thing for lead, I've got all these lead atoms, I'm counting them, 1, 2, all the way up to 6.02 times 10 to the 23rd, we would have this mass, 207.2 grams, right? So that's the same amount, the same number of atoms, but notice the helium, 1 mole of helium, 4 grams. 1 mole of lead atoms, 207.2. So yeah, and here's the explanation down there. So now let's take a look at a conversion factor. Now, we're going to need to be able to convert from moles to grams and grams to mole. So the conversion factor is the molar mass. Now, here are the steps to convert from moles to grams and grams to moles. First, calculate the conversion factor, or that molar mass. Put the desired unit on top of the conversion factor, cancel out the units, multiply across, divide top to bottom. So this is how we set them up, and there's 2 different problems we can do. Let's just go over them. Let's go from moles to grams. This one's an easier one. So this would be similar. Like this, setting up this is similar to knowing that you have 12 donuts and calculating the weight of those donuts. So let's just say I know each donut weighs 1 pound and I have 12 donuts. how many donuts do I have? Or what's the weight of those donuts? You know it'd be 12 pounds. So that's similar to what we are doing here. So calculate the mass in grams of 3.5 moles of water, H2O. So the first step is find the molar mass. Now we've already done this before. So look, I've already found the molar mass of water, 18.02 grams per mole. So what unit needs to be on top of the conversion factor? Well, it's asking me to find the mass in grams. So notice I've got 18.02 grams per 1 mole. So that's how I set that up. Which unit cancels out? So I want you to see what happens here, right? So I'm looking for grams. I need grams on top of my conversion factor. Moles cancel out. So all I do is I multiply 3.5 times 18.02 divide by 1, right? That's not going to do anything. And I get 67.07 grams of water. Now let's take a look at a trickier one. We're going from grams to moles. So this would be similar to knowing that you have 10 pounds of donuts and calculating the number of donuts. So calculate how many moles are in 50 grams of water. Let's go back to that explainer a little bit more, right? Similar to knowing that you have 10 pounds of donuts, and if each donut weighs 1 pound, how many donuts do you have? So if I know I have 10 pounds of it, each donut weighs 1 pound, I know exactly how many donuts I have. I'm going to have 10 donuts. So calculate how many moles are in 50 grams of water. What is the molar mass? Well, we've already found that, right? It's 18.02 grams per mole. Now, what unit needs to be on top of my conversion factor? I'm looking for moles. So notice that I've got 18.02. Well, those grams are going to be on bottom, and 1 mole is going to be on top. And because I need those grams to cancel out, because watch what happens, right? I need moles on top. The grams cancel out, so I take 50 times 1 divided by 18.02, and I get 2.77 moles of water. So that's how you set those up. So we asked this original question, how many molecules are in a bottle of aspirin? So in order to do this, we did this class activity called moles as the end of it. It's just practicing what we just learned. Now, this next question was sort of taking it to the next step. How many atoms are in a penny? So in order to do this, we did my 2 cents. And I'll go ahead and give you the verbal code at this time. The verbal code is 867. I say that again, the verbal code is 867. So in my 2 cents, you've got 2 different pennies, one made before 1982 and one made after 1982. Before 1982, pennies were mostly made out of copper, and they were 3.1 grams. So this one, what you were going to do is count how many atoms were in a pre-1982 penny. How many atoms of copper, right? So we know we've got 3.1 grams. We need to convert it into moles and then multiply it by Avogadro's number to get the number of atoms in 3.1 grams of copper. Now, after 1982, pennies were made smaller. They're 2.5 grams, but they're also made out of zinc. So you've got 2.5 grams of zinc atoms. You need to convert that to how many moles, and then multiply by 6.02 or 6.02 times 10 to the 23rd, or Avogadro's number, and you can calculate the number of atoms in a post-1982 penny. What is chalk made out of? So chalk is made out of calcium carbonate, right? So usually the ones like chalk is sort of a mineral. It's made out of like shells. Some of the chalk that we use is made out of calcium sulfate. We just said it's calcium carbonate because that's what the chalk and like that you find that's mined. That's what it's made out of. So we know that calcium carbonate. That's what we're using. So what we did was we had these chalk, and we went outside and we were drawing. So what we were going to do is we were going to use that. If we know the molar mass of calcium carbonate, we go out, we measure the mass of the chalk before we go outside. We go outside, we write on the sidewalk, we come back in, find the mass of the chalk after we write. We'll be able to count out how many molecules of calcium carbonate were left outside on the sidewalk. So that was chalk it up to luck. That was just a fun little lab to do, finding molar mass of certain molecules, calculating the conversion factor, finding moles, and finding the number of calcium carbonate atoms. So just a fun little way to practice everything that we learned. So this time I'll give you the final thought. Remember, there's just too much unknown in the universe to take a break from learning. Get out there and question everything.